Right, finish where you are on the thought process or the video or the drawing. Finish where you are right now. And now earphones out, or if you have headphones, whatever, earphones out. And I want you guys to discuss the first question within your group. Give any observations you can about the 3 main states of matter. Go. Take you less than a minute.
So, gas
All right, next question. Describe the shape of a phase diagram and try to indicate some key points on the phase diagram.
That's where they have equal densities, like liquid gas. Have lower pressure.
All right, and come back to me. What are the axes on a phase diagram? Pressure and temperature. Good. So we're going to start talking about how those factors play in the states of matter. Describe the shape of a heat curve. Draw it in the air for me. You guys aren't drawing curves, right? I really wish I could change this name too. Like, it's not a curve. It's a what? It's like a staircase, right? So we call it a heat curve, but it's a staircase. What do the plateaus mean? Phase change. What do the slatted parts mean? Changing what though? It's because what are the axes on a heat curve? Temperature and time, or temperature and heat added is another way. All right, so since you know what a heat curve looks like, draw a cool curve. Just right near your heat curve, draw a cool curve. On your paper, draw a cool curve. And label your cool curve. What's the top slanted area? What should it be? Okay, so temperature, time. First part would be what? Gas, and then it does what? What's that phase change called when you go from gas to condensation? So this is our condensation phase change. And then we go down to liquid, and then we do what? What's the phase change from liquid to solid? Freezing, that's what we say it. Like I said, some of this is your common sense or common knowledge that you've been exposed to. So the first part of this is chapter 13 material. When you're looking at reading guide 13, how'd you feel? Do you feel like it was familiar? Do you feel like it was really like unknown? The beginning, I mean, some of the like boiling point and pressure conversions will be new to us, but after that, like, it's just phases of matter. What do they look like? What do they do? What do we call a phase changes? How do we document on a diagram? So, go ahead and shut your computers. They're halfway shut, so I'm not compete with the internet. And I want you guys to draw, and this can be done on the same paper you're working with, because you already have some fantastic like outline of this, so we're just going to kind of apply all the concepts now together. So you have the background. We're going to apply the concepts together. Okay, so we have this big diagram. I'm going to make this a little bit more condensed. Right, solid, liquid, and gas. We're not going to talk about the process of converting to plasma, but I will give you some examples of plasma. Okay, what's the phase change of solid to liquid called? Melting. What's the phase change of liquid to gas called? Vaporization, or we could even say it's boiling, but that's a temperature specific thing. All right, and then as we think about all states of matter, we can go one way and the other way. So what's the process of going from gas to liquid? Condensation. And what's the process of going from liquid to solid? Freezing. Or crystallization or solidification. all those terms basically mean the same thing for us. There's one I'm missing. Where is sublimation? Where is the phase change occurring? Okay, so from solid to gas is when you go directly from solid to gas. You skip the liquid phase, that's sublimation. And what about gas to solid? It deposits, right? It's going to be a deposition process. So how many phase changes should we know? 6 of them between those 3 main states of matter. Examples of plasma would be like the aurora borealis. Has anybody ever seen that? Seen pictures, right? I tried to capture it on our national parks trip this summer. We tried to go out to the middle of nowhere on Dinosaur National Reserve or State Reserve on the middle of Utah where there's no lights. It's dark. It's one of the darkest places on the planet. And we tried to see the aurora borealis, but we drove like 24 hours. We just couldn't go. It was too late. So the process of forming plasma is through ionization of a gas. So you like make ions, and then they actually show off their colors. So the aurora borealis is an example of that. Or using the plasma balls. I don't even know it's called Spencer's anymore. Do you know what I'm talking about? Yeah. The plasma balls. That's plasma. You're basically you have a gas, and you're shooting electricity through it. So you're exciting them into ion form. Okay, so this information is relevant to part 1 of what you've watched. What I want to talk about is the effects of temperature and pressure on each of these states of matter. At least write solid. If you choose not to write the particle type, because you already have that in part 1, maybe you need to write down the motion. So take a minute and write down what you need to from this table. And we're going to talk together on pressure and temperature. This was on the bottom of the Google Doc. I know many of you did not even get that far, which is totally fine, but it is on the bottom of the Google Doc. You have to write down something. You have to write down what you need to. Write down something, at least the solid liquid gas, so we can elaborate from that. All right, come back to me now, okay? So we know a solid is a really, really, really tightly packed particulate diagram. So like you can't just put your hand through it because the solid particles are attracted to themselves. We maybe have thought about this before, or maybe I've said it before, but like the seat you're sitting in is solid, right? It's made of plastic. The polymer of the plastic is super, super, super attracted to itself. Therefore, your butt is not falling straight through it. But you're a solid as well, right? You're a solid. Your particles like your particles a whole lot. But what if the seat particles didn't like the seat particles, and your particles didn't like your particles? You could literally just walk through everything. I could walk through Ariane if her particles didn't like her particles as much as her particles like her particles. Because solid particles are they're just vibrating. That's it. They're really, really they're fastly moving. Not as fast as gases are, but they are moving the frequency. And technically, we could walk through solids if those particles just didn't have the attraction they had to each other, which would be kind of cool. But then you would just be like falling through floors and walking through walls, and people would be walking through you. Be kind of personal space invasion. So anyway, okay, so they do have vibrations because they are moving because of the kinetic energy that's naturally inherent. Now, if I took a solid like your pencil and I increase the pressure, what's going to happen to the volume of that solid? If I increase the pressure, what happens to the volume? I mean, try it on your pencil, guys. Increase the pressure on it. What's happening to the volume of your pencil? No changes. Okay, that's because particles essentially are about as close as they can get in the solid phase. So they can't get any closer. So if you increase the pressure, you're probably not going to change the volume. Delta means change. Remember that from way back? So if you increase the pressure on a solid, it's likely not going to change the volume just because they are so closely packed. You can't squeeze them together anymore. Does this make sense? Okay, so now liquid. How does the particle set differ for a liquid? Little bit of space. They're flowy. They can flow so that they're not locked in place next to each other. So I'll just kind of make them spaced out a little bit. We know technically they're even closer than that, but they have a little bit of space to move. So if I increase the pressure on a liquid, if I had like water and I could squish it, do you think maybe could happen to volume? It maybe would squish together a little bit, right? Just a teeny tiny bit. So if I increase the pressure, I could cause the volume to change a little bit. Just a teeny tiny bit. Because there's a little bit of space between the particles in the structure. You with me? Okay, we likely will not see that volume change because it's so minute, but it technically could happen. All right, and I did not tell you guys to bring your box of air today, but whip out that box of air. Whip it out. All right, you got this box of air, right? So there's all these particles inside. Increase the pressure on your box of air. Everybody, have your box of air out. Let's go. Increase the pressure on your box of air. Crunch it together. Okay, what happened to volume? What happened to volume? Everybody, what happened to volume? It didn't go away because we're not magicians, but it decreased, right? So what we have to know now is that increasing pressure will decrease volume. This is what kind of relationship? Is this a direct or an indirect relationship? Indirect relationship. And this is only for a gas, because how do gas particles look on a particulate level? Are they close together? They're loosely held together, so it's like boom, 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 boom. They're so far apart. What's between this gas particle and this gas particle, guys? What's between it? Nothing. Literally nothing. So if I'm trying to squish particle A towards particle B, there's nothing hindering them from getting close together. They want to be apart because they're high in kinetic energy. Those things are bouncing off the walls. But if I put the pressure on them, they can squish together. We can decrease their distances, aka their volume of the container. Okay, so those are the relationships between states of matter and the pressure applied. Which one is going to have a significant change in volume? Which state of matter? Gas, because they have the most space to play with. Another thing we should know is that the forces of attractiveness between each state of matter differs. So who's got the most forces of attraction? Right? Who's got the least force of attraction? Or the weakest would be gas. Good. All right, so all of these have energy. They're all moving at some frequency because the temperature that we exist at relates to the vibrations that correlate. All right, so these are those these little lines are supposed to be indicating the fast-moving particles versus the slow. And so if I'm trying to heat something, or if I'm trying to make something move faster, we should know that there's a relationship between temperature and kinetic energy. So write this someplace. Temperature and kinetic energy are related. What's kinetic energy, by the way? Energy of motion, right? So energy of motion. And which particle type moves the fastest? Gas naturally, and solids not really. They just kind of vibrate. So if I increase the temperature on something, I theoretically should increase the kinetic energy. So if I increase the temperature, I should increase the kinetic energy. And if I increase the kinetic energy enough, I'm going to cause a phase change from solid, which are kind of moving, liquids moving a little bit more, to gases, which are the highest of all the kinetic energy. So by increasing the temperature, I should be able to phase change. Were you with me? Okay. So now we have to talk about if the process of phase change is endothermic or if it's an exothermic process. I'm going to be quiet for a minute, read, and at minimum, write down the melting, freezing little section here. Read and write down some of that on the board. So we already know, like, the logic behind phase changes. We know that things naturally are going to change phase upon giving them energy. But we are assigning if that process is endo or exo based on how the energy is transferred or how the energy is applied. So what we will kind of have to recognize is literally you can change the pressure and the temperature of a specific substance, and you can force it to change phase from solid, liquid, gas to even plasma with energy. But we're going to focus not on the pressure for the moment. We're just focusing on the temperature, just to indicate the thermicity or the what's delta H stand for? Delta H is like last week. There's the E. Enthalpy, right, or enthalpy. All right, so we're looking for the specific, the heat exchange or the enthalpy exchange. Okay, so here's a solid. I'm just calling it solid X, and it's going to be transitioning or phase changing to liquid. Do you guys think? Okay, so hold on. Is this one moving fast or slow? Slow. So I'm going to put low KE, low kinetic energy right there. And what about the liquid? Low, medium, or high kinetic energy? Medium kinetic energy. So how would I get a low kinetic energy to a high kinetic energy? Would I add energy or take it out? Add it. So I'm going to add energy here. And so if I'm adding energy as a reactant, is this overall process a delta H positive or negative? Positive, because you're telling me it's a what kind of process? Endothermic. Good, because we put energy into the solid to make it turn liquid. We had to add kinetic energy to make it get to a higher kinetic energy. What about the opposite of this? If I'm going from liquid, which is what kind of kinetic energy? Medium. Manav, go stand up at the lab station. Back. And then solid here. Back with me. Low. Okay, so how would one get from medium to low kinetic energy? So take away energy. So energy in or energy out? Out. So I'm going to put energy over here as if it were being like released as a product. So would that delta H be positive or negative? Negative, and we're going to call that exothermic. So these are not reactions. These are processes. These are physical processes or physical changes. They are not literally reactions, so I'm not calling it an exothermic or endothermic reaction. I'm just calling it a process, just so we understand that's literally why I'm using that term. Okay, so what we should know is that there is a delta H associated with both of these processes, and it's called delta H fusion, also known as delta H fuzz as we abbreviate. Grab your notes, honey. This is not optional. Write down some of the stuff we'll write down right now, okay? At this point, the delta H fusion is what I'm going to write over here so you guys know this is the value for, notice this is for melting. So this value is specific to every substance in the world. So water has a value, methanol, alcohols, potassium, anything you melt would have its own value, but it would be a positive value. So what do you think the relationship between the relationship between these two values are? The number. So the energy I put in to melt something would be the same energy that came out of the same substance upon freezing it. So this value, these two values for delta H are the same, it's just one's positive and one's negative because of the process being endo or exo. So delta H diffusion is the amount of heat needed to freeze or melt 1 mole of said substance, whatever the substance is. We'll get back to these definitions. Can I pass this one? All right, so we've only done 2 phase changes, okay? So we're going to do the other couple. You guys do what we did for the first 2 for these 2 here. Write down little or low, medium, high. Write down your delta H's. We move all the stuff from your station back to that. right, Bailey's table, help me out here. What kind of kinetic energy does this liquid have? Medium kinetic energy, and this gas, high kinetic energy. And would you say this is a delta H positive or negative? Positive, because you have to put energy in to this process to force it to go to high kinetic energy. Therefore, it's endothermic. Front table up here, Bryce's table. What's the energy associated here? High kinetic energy, and then the other? Medium kinetic energy. What happened to energy? Okay, so the process is allowing energy to exit, or it's coming out of the reaction or out of the process. Delta H should be what? Negative. Exothermic. Okay, so let's write down an example for vaporization and condensation. Everyday life, write down 2 examples. One for the first, one for the second. You guys have an example for Riley's table? Either one. Okay, so like condensation of water on a cup. Anybody have one for vaporization? Boiling water, technically, right? All right, where would you guys put sweating? Like if it was hot outside and you started to sweat, which one would it be? No. Because when you are sweating, okay, I know water's coming out of your pores, or sweat and sodium ions and all that jazz coming out of your pores. But that's just the first step. What is the second? Why do we sweat as human beings? Okay, so what's keeping us cool about pulling water on our skin? Say again? It eventually evaporates, right? That's the actual process that's taking us to the point where we're going to survive and not overheat our bodies. So this is the example that they had one of these on the last exam, okay? So put sweating as an example. And what does sweat start off as? What state of matter? It's a liquid, right? And as it evaporates, what does it turn to? To vapor, to a gas, right? The state of matter of a gas. Okay, so how in the heck is this cooling us? What process is taking a liquid to gas? So it's going from medium kinetic energy to, over here somebody, high kinetic energy. So this is an endothermic process. So it means it's absorbing energy for this process to happen. So where is this reaction of sweating getting the energy? From where? Our body heat. So it's taking that heat away from us, cooling us down so we don't overheat and die. And the liquid is taking that heat, getting excited, and turning to what? To gas. So you should know sweating is an endothermic process, and it's specifically like a vaporization process or an evaporation process. Okay, so that's a neat example that you guys should remember. Okay, we'll do the last one. I'm going to come back to this definition tomorrow. Do this one, the last two, sublimation and deposition. All right, Corbin's table will help me out with sublimation. We're going from what energy? Low kinetic energy to what? High kinetic energy, so endo or exo? Say again? Endo, so this process requires energy, so we're putting energy into the process overall. Deposition, Kendall's table? High kinetic energy to low kinetic energy, what kind of process is this? Exothermic, so delta H is negative. All right, so let's write down an example for each of these. Sublimation and deposition. See if you can think of something first. There's only a couple that I'm assuming this is CJ's table, do you guys have an example? For either one? Maverick, you guys have an example? Where would dry ice go in here? So dry ice is actually CO2 going from solid to gas. So that is dry ice. So it's like a fog machine. Like on Halloween, it's basically dry ice, and they're vaporizing the gas and they're making it look like fog, or they're pushing the gas out to make it look like fog. Deposition. Anybody? Okay, this is a hard one. Something like frost. Okay, so like if you have water vapor in the air and it freezes, like on a crop or a plant or something like that, that's going straight from gas to solid. So frost would be a good example. Where would you put, you guys seen those like cone-shaped air fresheners?
Yeah.
Or where would that go? Air fresheners. If they all they do is sublime. Like they're solid, they're not melting. That would be gross. There's like resonant, that look like this pyramid shape. Any air freshener. They're solid and then they vaporize and you smell them. And you're like, oh, it smells good, but you never saw them go to liquid. So therefore, that would be a good example up here. Okay, and laptops up, go. Please log off. Do not just put your login over there. And oh, I have some people who have detention because they cannot put a laptop up in the right place and ensure that it's the right plug. So let's be very strategic this time so I don't have to give out more detentions. I need to see a couple weeks over this week. So it was a shame because it was a hot mess and my pregnant bug got on the floor over there and got down there and got the plug. So you guys are young and limber. Do it.